over this period of the beginning of the Industrial Revolution to last year. So you say, wow, why are we putting this up? That's not my fault. It's all my ancestors' fault. Wrong. Most of the damage was done since 1973. So all of you who were born before 1973, you are 100% responsible. You are 100% responsible. Okay? If you were born after 1973, you're partially responsible. The only people who are innocent are those babies that are posted on the bulletin board. And how long do they have before we reach this 450? If we have business as usual, 23 years. Okay? So if you want to be responsible to those people so that they don't see real disaster when they're 23, just graduated from college, we better do something. And what is that something? So you say, well, I don't live in the UK or in the US. Well, wherever you live, do that. That's your share of the carbon budget that's been used, okay, per person. Now, here's Taiwan, here's Korea. It's roughly the same as Japan. Japan used more in the past, but it's been very good in the recent past until Fukushima. And Taiwan and ROK is about there. It's not the worst, but it's not very good. That's the responsibility of everyone in this room. Okay? So, climate discussions are underway in Paris, and everybody has submitted their INDCs, which means intended nationally defined contribution. So each nation says, here's what we think is our fair share. Nobody actually is looking at this, but it's in the background. And each nation has to find its own solutions. Okay? So what can we do as scientists? Well, we need to find better options. The options that are put before the table now are all those that failed. Okay? If we've had 40 years, nothing has helped. So are we going to try another 40 years? And isn't that the definition of insanity? To try something that obviously has failed? As scientists, we have a responsibility to try to find better options. Okay, that's our responsibility, I think. Okay, so let me give you a SWOT analysis of old versus new nuclear fission. I'm talking about fission, not fusion. So we're using neutrons to initiate reactions rather than having charged particle reactions. That makes all the difference in the world, whether it's doable in a short enough time. With neutrons, you could have the reaction at ambient temperature, or 500 degrees or 1,000 Cs, something that you can hold in metal containers. With charged particles, to make them come together, you need 10 to the 7th degrees at the center of the sun. We're not nearly as dense as the sun, so you need 10 to the 8th degrees. Well, no container can hold a plasma at 10 to the 8th degrees. So you've got to hold it with magnetic fields, or you've got to use lasers. All of those are unstable. So at best, even if we can show break even, in the beginning, fusion is not going to be a power source. You're going to get a millisecond of power, and then you're going to spend the rest of the day for the next day's shot. Okay, that's not power. It's going to take a long time. It takes a long time for any of these technologies to develop. When coal had its day, right? It took that long. It just takes 50 years, 100 years. What makes us think, with nothing to stop it, money to be made, that we can do now things where it's not clear there aren't things that will stop it, or that money may or may not be made. So this is the problem that faces us. Okay? And let me just say that my motive here is not to try to find blame. I think we've got to get past that. Everybody gives an excuse why their technology didn't work, okay? Time has passed for excuses. Who cares what the excuse is, okay? The excuse is usually of the form, somebody evil stopped us. That doesn't help, okay? There's nobody evil. Everybody's trying to do their best. So it's time to stop blaming people and trying to find solutions, okay, in a constructive way. If there's technology is not good enough, try to help them make it better. So let me describe nuclear fission to you. There are nuclides, nucleus, atomic nuclide. I call it fissile. They're considered fissile. Generally speaking, they're nuclei with even numbers of protons and odd numbers of neutrons. So U-235 is such a thing. The odd neutron is such that if you add a neutron to it and it has opposite spin, you get an extra 1.5 MeV roughly. And that's enough to cause it to vibrate, even at 0 temperature, vibrate apart and release binding energy. Okay? And the only fissile that exists naturally is U-235, and it's only 0.7% of natural uranium. So if you have a fissile and you add a neutron to it, it would probabilistically split into 2 pieces. These are called fission products. They're usually going at tremendous speeds, not anything close to the speed of light, but much faster than normal terrestrial speeds. And the energy is mostly carried in those 2 charged fragments. They just kind of leave their electron clouds behind them when they fission. Timing things, I'm obviously running a little short. And when they come apart, they have more neutrons than when they like as small fission fragments. So they will spit out 2 or 3 more neutrons. 99% of them come out immediately, within a microsecond or less. Okay? There's no way you can control this. 1% of them come out slowly, millisecond, minutes, some even longer. Okay? Those are what are used to control nuclear reactors. So you make it have a subcritical mass with respect to the prompt neutrons, make it critical, exactly critical with the ones that you control. And so it's just running, neither exponentiating nor decaying, all right? So since you have 2 or 3 neutrons spit out, you need one of them for the chain reaction, and then the other can actually make fuel what was not previously fuel. For example, you can make plutonium-239, which is, again, even odd, from uranium-238, which is obviously even, and is 99.3% of uranium. What happens if you add a neutron to uranium-238, becomes uranium-239, too many neutrons compared to protons, so 2 of them beta decay, 1 at a time, until you get plutonium-239. So that's plutonium. U-233 is also possible by adding a neutron to thorium-232, which is 100% of thorium. Thorium only has 1 stable nucleus, naturally occurring, thorium-232. And so when you add that neutron, it becomes thorium-233, even odd, too many neutrons again, and so it beta decays and becomes uranium-233. Okay? Now here is what happens, how many neutrons are spit out as a function of the neutron that it captures. And you can see that it's a number that goes between 2 and more than 3, all right, as I said. And the one that's best, if you want really very slow neutrons for reasons we'll discuss, is uranium-233. So the thorium cycle is best. Otherwise, you have to use very hard neutrons coming out at, an MeV or more, where plutonium is very good. So plutonium is good for fast breeders. Thorium is good for thermal or slow breeders, okay? And there are reasons why you would prefer slow to fast. And here's the reasons. If you look at the cross-section of any of these, so here's the fission cross-section of uranium-233. You come in with a neutron, you emit a small fission product and a large fission product. Usually they're not exactly equal in size. And the cross-section as a function of energy in EV is like this. Generally speaking, it has a slope of e to the minus 1/2. And then there's a whole bunch of resonances, okay? And then it does something funny at high energies. What's this e to the minus 1/2? That's 1 over velocity. You can think of it the following way. Nuclear reactions are short-range interactions. So they're only important as the neutron passes through the nucleus. Okay? The time that it takes to pass through the nucleus of a given size is 1 over the velocity, proportional to 1. And so the more time you have, the more likely you're to initiate the reaction. So it looks like this. What are these resonances? Well, a pack of neutrons and protons is a many-body problem. If you play pool, you will know that it has normal modes. If you shoot the pool ball in there very slowly, it can absorb that neutron at the expense of jiggling these balls. There are many, many ways of jiggling those balls, okay, and bring that pool ball to rest. Those are resonances, okay, internal and body resonances. And they all look like this, all right? Uranium-235, here's the fission cross-section. Here's plutonium. Wow, it's got huge cross-section. That's why the first generation of nuclear physicists like plutonium, okay? Makes good bombs, for example. Right? But here, you see something troubling. And that is that uranium-238 does not always, or even close to always, capture a neutron to become uranium-239, all right? It actually has a reasonable cross-section of going on to other things, okay? I didn't show it, where you end up with an even nucleus, so it's not useful for much. Let me show that to you. So here is a plot. Professor Ting will recognize this plot, okay? All astronomers should know this plot. If you want to talk about nuclear reactions, whether in stars or in a nuclear reactor, you plot the number of protons versus the number of neutrons, okay? So if you start with uranium-238, for example, you can capture a neutron to become uranium-239. It beta decays twice to become plutonium-239. Now, you would like it to fission if it captures another neutron, but in fact, for each time it fissions, about 0.6 of the time, it captures a neutron and becomes plutonium-240. That's no use. So you have to capture another plutonium, it becomes plutonium-239, can do that or can do this. Whether it goes on to capture another neutron before it beta decays, that's called in astronomy a R process if you capture a neutron, whereas this is S process because as soon as you can decay, it decays. Okay? So you can see that burning uranium-235 that has uranium-238 produces a mess. You produce a lot of things besides the stuff that you want. Some of them can come back down via alpha decays. So it's a big mess. It's very hard to reuse this waste. It's not impossible, but it's difficult. Whereas thorium-232 is different. It captures a neutron. It's high. This is a very short decay, a short, fast decay, so quickly becomes protactin-233. There's a slight chance that it could capture another neutron, and we'll discuss that branching probability, but it's only about 8% of the time. Most of the time, it will come this way, okay, to uranium-233, which will most likely fission. But, I'm sorry, the 8% was actually for the next step. But 8% of the time it will come here, and you have to go here before you can fission. And then it has a small chance of becoming uranium-233. But this is a very small cross-section, okay? So it basically dead ends at uranium-236. Now, proliferation from nuclear reactors by building weapons is not possible if you build your reactor properly, either fast reactor or thermal reactors. And the reason is because here you form lots of plutonium-240. Plutonium-240 can spontaneously fission. Okay, it's so big. It can spontaneously fission, throw off neutrons. And that's very bad for a bomb because before you're ready, it blows up. Okay, so nobody will build a bomb this way unless you have incompetent scientists. Okay, so reactors do not build bombs. all right? Unless you do something special. Breeding U-232 also does not build bombs because U-232 can sometimes, when you have fast neutrons around, come in with one neutron, knock out 2 neutrons, becoming thorium-231, which will then typically follow this path, which will produce uranium-232. What's so difficult about uranium-232? When it decays, one of its products is to produce a 2.6 MeV gamma ray. That gamma ray is deadly. If you try to build a bomb, you'll die within an hour and a half. If you try to make any timing device, it'll just burn out your electronics. So that's the proliferation resistance here. Okay.